So we found out then that our string has a series of resonant frequencies, particular frequencies at which it would most like to shake. And each of those resonances is associated with a particular shape of motion of the string. We can describe the shape of the motion of the string, if we like, in terms of the wavelength of the wave that's created. So our fundamental has the longest wavelength, twice the string length. Our next mode, which we sometimes call the second resonance, or you'll hear people call this the second harmonic, or the second frequency of this string. You can see it's a shorter wave, right? In fact, it's a wave that's exactly half the wavelength of the one above. So this one gets half a wavelength from here to here. This one gets half a wavelength from there just to the middle of the string, right? So if the wavelength of this is twice the length of the string, the wavelength for this second resonance is exactly the length of the string. There's a whole wave. For the third resonance, we can see a whole wave just to there. So the wavelength is not even quite a whole string length. In fact, it's 2/3 of the length of the string. For the next mode, I didn't show you guys this one, but you could guess what it looks like. For the next mode, the wavelength is exactly half the string length, and then 2/5 of the string length. In fact, you can guess from here what the wavelengths of all of the resonances are. So I've got 2L/1, 2L/2, 2L/3, 2L/4, 2L/5, 2L/6, 2L/7, 2L/1,000,006, right? Okay, so I've got this whole series of wavelengths, and from that series of wavelengths, these spatial patterns, I can figure out what all the frequencies are, what all the pitches are of the notes that this string would play if it were shaking in one of these particular resonances, right? So how do I do that? I remember that to find a frequency, I take the speed, divide by the wavelength. So that's all I've done here. So V/2L. Here's V over this wavelength, 2L/2. Here's V over this wavelength, 2L/3. And what you'll notice here is that the frequencies of the vibrations for these particular resonances are related to each other in a beautiful and simple way. In fact, all of these resonant frequencies are just multiples of the lowest one. So if I have a string that wants to shake up and down, the lowest frequency I'd like to shake up and down at, let's say, is 40 Hertz. That's this one. Then we know that the next mode will be at 80 Hertz, and the next one at 120, and then the next one 4 times 40, 160, right? And then 200 Hertz, right? So as soon as you know this frequency, you know the frequencies of all of these harmonics, and this is a series of multiples of exactly whatever it is that your fundamental frequency is going to be. Okay, so we've made a lot of progress, right? We figured out what sound waves are. We figured out what frequency means. We know that frequency tells us about pitch, and we know what physical properties of the string determine its frequency and therefore determine its pitch. But I claim that I have not told you anything deep, because we have two problems that we haven't dealt with at all, and I think that they're both kind of important. First of all, when we talked about figuring out how to raise or lower the pitch you hear when you pluck a string, we only talked about this lowest resonant frequency, right? But there's all these other ones. How come they don't tell us what note we get when we pluck the string? How come we only got to think about this one when I said that the string was happy to vibrate in any of these kinds of motions? So that's one question. And the other question is, what about different instruments, right? If I have a violin and a piano playing the same note, like exactly the same pitch, you can tell which one is which, right? You can tell this is a violin, this is a piano, and this is a trumpet, and you would never get confused. Even though they're playing the same frequency, the same pitch, there's something about the tone quality, we sometimes call the timbre of the sound, that is different from instrument to instrument. So it turns out that these two ways that I have let you down by not telling you about how to deal with these multiple resonances and by not telling you about different instruments, they go together. The answer to both of those questions is the same. And to think about what the answer is to what do we do with the multiple resonances, and how do we figure out the timbre of an instrument that distinguishes one instrument from another, we need to look at the actual sound waves produced by real instruments. Oh, so there's violins. There's the back of a violin with its resonances made done with sand, and that's a tuba. Okay, so these are sound waves produced by real instruments, and they're all playing the same pitch, the same note. Okay, so this one is a soprano, this one is a piano, and this one is a factory whistle, all playing the same note. And again, what you're looking at here is one of these traces that shows you the way a microphone is moving in time. So this is the actual sound wave pushing on the microphone as it comes up to its surface. So this is reflecting the compressions and rarefactions of the air created by each of these instruments, the soprano, the piano, and the factory whistle, with whom I'm sure the soprano would rather not be compared. Okay? So that's what we've got. Why do I say these are the same frequency? So to figure out whether they're the same frequency, you want to actually look at the whole shape of the wave, this complicated wave, and see how many times the whole wave repeats. So here I've got 1, 2, 3 of the whole complicated shape. Here I've got 3 of that shape, and here I've got 3 of this shape. So the overall frequency, the overall number of waves per second is the same. Okay? But the shape is completely different, right? The shape of each one of these individual cycles is completely different between these 3 instruments. So how do we actually get complicated waves like this from the resonances of an instrument? Here's how to think about it. Let's go back to our string, because we understand our string. If the string is just shaking back and forth in one of its resonant motions, say just in the fundamental, it will make a very simple sound wave. Just this one. No extra wiggles, no bumps, no elephant shapes, just this simple wave, okay? And similarly, if it's oscillating in any of these pure resonant motions, you'll also get a very simple sound wave. They're very simple sound waves with different frequencies, so this is 3 cycles, this one's 6 cycles, that one's 9 cycles in the same amount of time. But they're all just simple oscillations. None of them have the complexity that the voice or the piano or the whistle produces. However, I can make a complex wave like that by adding them together. So this red wave I have on the bottom, which begins to look like the sound produced by a real instrument, it's got some overall repetition time, and then it's got a bunch of extra funky wiggles that make it some interesting shape. That wave came just by adding up these 3. And that kind of tells us what's going on inside a real instrument when it's shaking the air. It's not just vibrating in one of these particular resonant motions, it's vibrating in some combination of them. So in this case, it's looking like I'm getting some, if this is the wave that comes out, it means I'm getting some motion like this, added to some motion like that, and then also some motion in the 3rd harmonic. Okay? So that's what we've got in real instruments. And to kind of try to convince you how that works, I've got a couple of little sound clips that we can try. So this is the note from a clarinet, followed by the pieces of that note taken apart that correspond to the individual resonant motions of the clarinet. So first you'll hear a clarinet, and then you'll hear a series of tones which correspond to the individual resonance motions for the clarinet tube. Okay, so all those really high notes in there, those are the high harmonics of that fundamental tone, which you associate with the pitch that you hear, and they're all packed in to the note that the clarinet makes, and they help us recognize the timbre of that note as definitely being clarinet. One of the things you'll notice about this complicated wave that's created by adding up these 3 simple waves is that its overall frequency, the total number of bumps I get here in this amount of time, is the same as the fundamental. I've got 3 of these complicated wave shapes. I've got 3 of those simple fundamental ones. So when you take the fundamental and you add in motions from the higher resonances, you still get a note that sounds like it has the frequency of the fundamental. It has the pitch that's set by that lowest resonant motion. That's why it was okay for me to talk about changing the pitch of the violin by thinking about what frequency we get just for that simplest fundamental motion. But then to figure out the shape of the wave, which allows us to distinguish between sounds made by different instruments, we need to think about how the motions from the other harmonics are mixed in.